Okay, we basically finished the relativity portion of the course, and the remaining three, some sense, independent modules: the tensor formalism of general relativity, black holes, and cosmology. They're really three independent components. Therefore, we can study any one of them without learning the others two. So I've decided to put the last chapter 11, here, so that the student interested in the math part will have a chance to see it, because we just finished learning the general relativity, and um, then we will talk about black holes and the cosmology. And so for the tensor formalism, we're first going to review the coordinate transformation, which we already seen discussed in chapter 3. And then we're going to talk something called covariant derivative, which is a key concept in differential geometry. And then showing the Christoffel symbols, how it's related to metric tensor. And then we'll talk about the parallel transport, and also talk about geodesic in a proper way. Uh, in our physics first approach to GR, so the math result will stay without proof. Riemann curvature tensor was shown to be this complicated looking object with first different derivatives back to the Christoffel symbol and the Christoffel symbol squared. So it's a nonlinear second order derivative of the metric tensor. And the Christoffel symbol, again, just given to be related to the metric tensor. And we never show how is Christoffel symbol should be related to the first derivative of the metric tensor. Okay. Then we talk about Einstein tensor had this combination of tensor reaches scalar, has just a geometric property to be part of the Einstein equation, and we're going to come back to show this how to derive this property. And then even for geodesic curve, we only derive the equation through the condition of extremization or minimization of the length, and but did not properly study as property as the straight line, and which we started in box 5.2, but it's incomplete, and we're going to do it much more efficiently once you know the tensor in GR. Okay. And also, of course, we said geodesic equation should be the equation of motion for GR. It's very plausible, but it's nice to have a formal proof. All this can be done once you know something about the tensors in general relativity. Basically, key point is this covariant derivative. Tensor for general relativity and special relativity are basically the same. Okay, their differences show up only when the operation differentiation is performed. Okay. This complication arises in GR because the curve space, basis vectors, the metric, and the transformation matrices are all position dependent. So therefore, we'll make it some differential operator had to be taken care of properly in order to not spoil the tensor property. And of course, GR requires the physics equation to be covariant under general coordinate transformation, and that leaves invariant ds squared. So just like we learned in rotational and special relativity, in order for physics equation to be tensor, if you write physics equations as tensor equations, then they automatically respect the Lorentz symmetry or rotation symmetry. It's the same way. GR equation must be tensor equations in order to respect the general coordinate transformation. So that's the principle of general relativity can be fulfilled automatically. Yes. So once you know how to write tensor under these various transformations, then automatically gets the proper relativist equations. And that's why we absolutely need to know how to use tensors. Remember, we say tensor components are expansion coefficients of a tensor in terms of basis vectors. Okay? Under coordinate transformation, a tensor itself does not change, but its component changes because the basis of is transformed. And now, of course, we keep referring to tensor components. It's a whole mouthful. So we often will simply say tensors when we mean tensor components. There's really no confusion because in the context it's pretty clear that we mean tensor components. And if necessary, of course, we emphasize we're talking tensor, not tensor components. And for both GR or special relativity, the transformation can always be written as partial derivatives. Okay? Because from a chain rule differentiation, for example, dx mu transform as this partial derivative because by the chain rule differentiate. And the del operator transforms as a partial derivative because, again, partial differentiate. This is, of course, the inverse of this transformation. So we can interpret these as transformations of the dx prime, delta prime, and through these are transformation matrices written as partial derivatives. And also clear they are inverse to each other. Okay. And remember we said the contravariant covariant components, the contravariant was upstairs indices, covariant downstairs indices, transforming the same way. The contravariant component transforms the upstairs mu, the x mu, and downstairs covariant component transforms the del operator with index mu. So it was the contravariant component transformed the same way as the differential, and the covariant components transform the same way as the del operator, the derivative operator. And also said we can explicitly write out the transformation matrix with elements being partial derivatives. Here's an example of a covariant component transformation to the primes and to the partial derivatives. Now, keep in mind that when we're talking about transformation, we're talking about transformation of the components. The tensor itself, or the vector itself, A, is coordinate independent. Now, when expanded, vector A is expanded into the basis coefficient expansion. For the in terms of base vector, you have contravariant components. In terms of the inverse space, we have the covariant components. So because the left-hand side does not change under coordinate transformation, so therefore whatever change of the coefficient expansion must be cancelled by the transformation of the base vector itself. Okay. In fact, to cancel means it must transform in inverse way. So therefore, knowing the fact the contravariant component transform this way, so therefore the base vector must transform the opposite way. Okay. Here dx prime dx, here dx prime. Same way it goes for the inverse spaces, transform same way as the covariant components. In fact, that's the reason why A sub mu is called a covariant component, because they transform in the same way as the basis vector. Okay. And so this transforms the same way as the base vector. And the contravariant components transform in opposite way. That's what we call contravariant components. Also, base and the inverse basis vectors are orthogonal to each other. So therefore, we can use in this property to project out the coefficient expansion. For example, if I dotted the inverse basis into this expansion here, then because the base vector become 1, so therefore the projection of the vector onto the inverse basis is the contravariant component. And same way, the projection of the vector onto the base vector are the covariant. And this also makes it clear why this is called covariant, because the covariant component is directly related to a basis vector multiplied by something which doesn't change. So therefore, they must transform the same way. Same way, the contravariant component is directly related to the inverse basis, so therefore must transform the opposite from the basis. Now we only talk about vector, which is tensor of rank 1. For higher rank tensors, the more indices, and you just expand the same way. But particularly, just to remember, is that tensor components, component of a higher rank tensor have several indices. They transform the same way as product of vectors. Okay, so like this case, you have two absurd indices. They transform product of the contravariant component. Have one I display one lower indices. They transform also product of the covariant components C sub lambda. In particular, for example, we talk about a case with one abscissa indices, one downstream indices, then transformation is because transform like one contravariant component times one covariant components, and the contravariant component transform this way, the covariant component transform this way. So therefore, the T mu union transform two transformation matrices that they multiply, and one is del x prime, the other one is del x prime del x. So we can easily work out for general cases. In particular, for the metric tensor, which have total low indices, then it transforms with two transformation matrices, each is del x prime, del x prime. Now, more about the metric tensor. The metric tensor are directly related to the basis, like this, okay, and inverse is the inverse basis. So therefore, in a curved space, because the basis must necessarily change from point to point, so position dependent. Hence, the metric, because the metric directly expressing curved basis, must be also position dependent. And if the metric is position dependent, the transformation, look at this transformation equation. The left hand side, right hand side, the metric both be position dependent. So therefore, the transformation matrix must necessarily also be position dependent. So therefore, coordinate transformation in the GR, in the curved space-time, must be necessarily position dependent. That introduces some of the complications we can see. So it's the end of first part of lecture 16.